Welcome to Algebra 2. Today we're working in 3-5 and we're going to be talking about the zeros of polynomial functions. Now, a zero of a polynomial function zero is the value of the polynomial or an x value that's going to cause the polynomial to equal 0, or in other words, make the y value equal to 0. Now, on a graph, and I'm talking about a graph of all the real numbers. If your polynomial has a 0, that would be a real number. So let's just sketch a graph of a polynomial here. Then the zeros will show up as x-intercepts. Only the real zeros, though. If there are complex zeros or imaginary zeros, you will not see them on a graph. You'll have to calculate those by hand. But we'll talk about today about what those real zeros look like and how can I use those real zeros to do things like sketch graphs, how can I use those real zeros to solve inequalities and interpret word problems. So first of all, let's talk about how I can use the zeros to sketch a graph. So up until this point, every time you've seen a polynomial and you had to graph it, the only way that you could do that would be to pull it up on Desmos. Well, Desmos is fine, but there's also, you can kind of sketch a quick graph of a polynomial by hand without having to pull up Desmos every single time, or a graphing calculator. But you only need to know 3 things in order to graph a polynomial. The first thing that you need to know is you need to know end behavior. And so you'll want to refer back to your 3-1 notes on the end behavior. And remember, you'll find your end behavior by looking at the leading coefficient and the degree. Then you'll need to know your x and your y intercepts. So to find your y-intercept, you're going to need to let the x be 0 and solve for y. For the x-intercept, you need to let the y equal 0 and then solve for x. Then you'll need to figure out something about multiplicity, which is repeated zeros, and we'll explore that more in the next example, but these first 2 graphs are based on those first 2 ideas of end behavior and x and y intercepts. So on example 1a, let's look at the graph and let's come up with a sketch. So a is f of x equals 4x cubed plus 4x squared minus 24x. So the first thing we need to do is we need to figure out the end behavior. Well, I'm looking at this, and for my end behavior, I see that the leading coefficient is positive, and the degree, because my leading coefficient would be 4, the degree is the highest exponent, the degree is odd. So since the leading coefficient is positive and my degree is odd, that means the bottom is going to point down and the top is going to point up. Now let's look at our intercepts. Let's find the y-intercept first. For the y-intercept, I'm going to let x equal 0. And I'm going to substitute 0 in for each x in my equation. So y, which is what we're saying f of x is. Come on now, y equals 4 times 0 cubed plus 4 times 0 squared minus 24 times 0. Well, 4 times 0, 0, plus 4 times 0 is another 0, minus 24. So my y-intercept is at 0, 0. Let's highlight what we figured out so far. So we figured out our end behavior. We figured out our y-intercept. Now let's find the x-intercept. Well, to find my x-intercept, I need to let the y equal 0. So let's erase that so I can see the problem better. Okay, so the y is the f of x, so I will say 0 equals 4x cubed minus 4x squared minus 24x. And I need to solve for x. So I see that there are 3 terms. I'm going to solve by factoring. And I look, and the first thing I see is that there's a greatest common factor, so I'm going to factor out a 4x. When you factor out 4x, you're left with x squared minus x minus 6. And let me double check that problem. There was a plus right here. Plus. Okay, then I see that I can factor that trinomial a little further. So 0 equals, bring down the 4x, factor the trinomial, x times x is x squared, and then 2 numbers that multiply to be negative 6 and add to be 3 would be positive 3 and negative 2. So then I'll apply the zero product property, set each factor equal to 0. So if you set 4x equal to 0, then x equals 0. If you set x plus 3 equal to 0, then x will equal negative 3. And then if you set x minus 2 equal to 0, you'll get x equals 2. So now I have 3 x-intercepts. I have an x-intercept at 0, 0, another one at negative 3, 0, and another one at 2, 0. And let me highlight that. All right, so that should be enough information I'll need in order to graph or sketch a graph of that polynomial. So I will sketch a graph, sketch in the x-axis, sketch in the y-axis. Now I'm going to plot all my intercepts. I know that there is an x or a y-intercept at 0, 0, but also an x-intercept there. I know that there is an x-intercept at 0, 0, which I've already plotted, an x-intercept at negative 3, 0, and then an x-intercept at positive 2, 0. Now remember, this is a sketch, so we're just going to get an idea of the basic shape of the function. But we do know that the left side points down from the end behavior and the right side points up. And then in between, I just have to connect the dots. So I'll cross up here, go down, and then come back up. Now this section right here, it could go up really high or it could stay pretty close to the x-axis. I'm not sure. All I know is that it has this basic shape, and then if I want to be even more sure, I can pull up a graphing calculator and graph it that way. So now let's talk a little bit about the second one, part B. So let me erase this. Let's do the second one, because something interesting pops up in the second one. We've got that x to the 4th minus 81. There we go, erase. Okay, so first thing I need to do, figure out the end behavior. So my end behavior, x to the 4th, start off with black here. End behavior. For end behavior, I'm going to look at my leading term, has an even degree. And the leading coefficient, the number in front, is a 1, which is positive, so I have a positive leading coefficient. So since it has an even degree and a positive leading coefficient, that means that both ends are going to point up. So highlight that because I'm going to need that information. Then I'm going to find my x and y intercepts. So let's find the y-intercept first. Remember, with the y-intercept, you're going to let x equal 0. So when I let x equal 0, y equals not x to the fourth, 0 to the fourth minus 81. So y equals negative 81. So I have a y-intercept at 0, negative 81. This is really going to be a sketch here because that scale does not go down to negative 81, so I'll just have to change the scale. For the x-intercepts, and remember we're going to talk more about multiplicity in the next part. All right, for the x-intercepts, that's where you let the y equal 0. So I'll have 0 equals x to the fourth minus 81. And I'm going to factor this to solve. So I notice I've got two terms. And it's a difference of perfect squares. So that will factor into x squared plus 9 times x squared minus 9. And then x squared plus 9 is a sum of cubes that factors into x plus 2i times x minus 2i. And then x squared minus 9 factors into x plus 3 times x minus 3. Not 2i. My bad. X plus 3i. I can't take a square root. And x minus 3i. Let me erase the rest of this work down here. So then I'm going to set each factor equal to 0. So if I set x plus 3i equal to 0, I'll end up with x equals negative 3i. And x minus 3i equals 0, x equals positive 3i. X plus 3 equal to 0, x equals negative 3. X minus 3 equal to 0, x equals positive 3. All right, so I've got two imaginary x-intercepts and two real x-intercepts or zeros. Now the imaginary ones, they are not going to show up on my graph because my graph only shows the real number coordinate planes. So you will not see these. So you don't graph these. But I will see an x-intercept for negative 3, 0, and another one for positive 3, 0. So let's just, since our y-intercept is so far down, let me just draw a sketch out to the right here. That way I don't have to worry too much about all those individual graph tick marks. Okay, so let's see. I see that there is a 0 at negative 3, 0. So I'm just going to put a point here and call it negative 3. 1 here and call it positive 3. So x-intercept, x-intercept. A y-intercept at negative 0, negative 81. So let's just call this negative 81. As long as I label it, it should be okay because remember, I'm just sketching. I know the ends are both going to point up. I'm not sure what's happening in the middle, but I just need to like connect it. So it could like do some weird loop-de-loops at the bottom, but it just needs to come down, hit negative 81, and come back up. Now if you want to see what the exact graph looks like, pull up Desmos and graph that. All right, now let's talk about multiplicity. So this is the third thing I said that you need to know about whenever you're trying to draw a graph. Multiplicity is how many times a particular number is a 0 for a given polynomial. So let me show you what I mean by that. On example A, I have f of x equals x times x plus 4 times x minus 1 raised to the 4th power. Well, another way to say that is that f of x equals x times x plus 4, and then x minus 1 to the 4th, I could write that out 4 times. And then if I were to find the zeros, I would set f of x equal to 0, and then I would solve by factoring, but I'm just copying it all down right now. Then I could apply the zero product property to each factor, so I would say 0 equals x, 0 equals x plus 4, and so on. But I would end up getting all these answers. I would get here that x equals 0. For this one, I would get x equals negative 4, because when you set x plus 4 equal to 0 and solve, you'll get x equals negative 4. For this one, I would get x equals 1. Then I would get x equals 1. Then I would get x equals 1. Then I would get x equals 1. Okay, so you notice I got x equals 1 4 times. This is what we call a multiple zero, because that number repeats that many times. So if I were to list the zeros of this polynomial, I would say that x would equal 1, but then in parentheses, you might be asked with a multiplicity of 4, because that 0 appears 4 times. Now you don't have to do all this work every single time if you're looking for multiplicity, because if I want to say with a multiplicity of 4, all you have to do is look at the exponent, and that will tell you what the multiplicity is. And if there's no exponent, remember that when there's no exponent, then the exponent is understood to be a 1, so the others would have a multiplicity of 1. So x equals 0 would have a multiplicity of 1, x equals negative 4 would have a multiplicity of 1, but x equals 1 would have a multiplicity of 4. Now, how does that affect the graph? Look at this part. When the multiplicity is odd, the function crosses the x-axis at that 0. Cross meaning the function actually crosses the x-axis, like right here. Then, when the multiplicity is even, the function has a turning point at that 0. And you'll see Savas call it as touching the x-axis, touching meaning it would like hit the x-axis and turn around. So here's a picture of what that would look like. So x, y, and maybe my graph would look like this. So like right there. Turning point on the x-axis. Or Savas would call it touching. So let's sketch the graph for part A so that we can get an idea of what's happening here. To wait while we erase. Okay, so we said there are zeros at x equals 0 has a multiplicity of 1. X equals negative 4 has a multiplicity of 1. And then x equals 1 has a multiplicity of 4. Okay, so I'm going to draw an x and y axis. Whoops. Okay, at x equals 0, there's an x-intercept. At x equals negative 4. And then at x equals 1. There's a point here. There's a point there. Then I'm also going to need to know the end behavior. So I'm going to look for end behavior here. Let's grab a highlighter. Okay, so to get end behavior, I need to know the leading term. Well, that leading term happens whenever you multiply the x's together. So I'd multiply this first x times that x times this x to the fourth. So x times x is x squared, and then the x to the fourth I would have would be x to the sixth. So my leading term would be an x to the sixth, which is even with a positive leading coefficient. So both ends are going to point up. Okay, so up on this end, up on that end. And these are supposed to be curvy lines, but my stylus is making them kind of wavy. So let's see if I can draw a little bit better with a marker. Nope. Just kind of looks like I'm shaking a little bit. Maybe I'm nervous. Okay. So at x equals, let's see, where am I at? -4. Multiplicity of 1, so I need to cross the x-axis. And then at 0, multiplicity of 1, I need to cross the x-axis. So I'm just going to cross there. Then at x equals 1, oh wait, hold on, let's start over. Start over. Both ends point up. Man, I'm wanting to go cubic on this. Both ends point up. End behavior. Make both ends point up. Just don't make them so wavy. Try this again. Don't make them so wavy. Okay. X equals -4. Multiplicity 1, cross the x-axis. X equals 0, multiplicity 1, cross the x-axis. I'm just going to connect them. And then x equals 1, multiplicity of 4, so it touches. So I just got to curve it and make it touch. And there we go.